Okay, so let's just go through equilibrium once more. So at equilibrium, suppose we have this general equation. AA plus BB goes to CC plus DD. So reactants and products. So my equilibrium expression, and you'll hear us say, what's the equilibrium expression? You just write that K is equal to products over reactants. And then you write down K is equal to the concentration of our products to the power of the coefficient, concentration of the product to the power of the coefficient, over concentration of my reactants to the power of the coefficients. So this is called my equilibrium expression. The K is my equilibrium constant. Remember, if you see us put down a subscript of Kc, that means all of my reactants and products are expressed in terms of concentration and molarity. And in fact, we want this to be in molarity. So equilibrium expressions should be either in molarity or in partial pressures and atmospheres. You can't do it in moles, can't do it in any other types of units or expressions. Okay, so let's go through and just summarize the characteristics, okay? So, recall the characteristics. So, at equilibrium, okay, the concentrations of reactants and products no longer change with time. Okay? So that's really important. So when we state this, it no longer changes. So in the initial part, we're not at equilibrium, my concentrations will change. But once I hit equilibrium, they no longer change. Okay? For equilibrium to occur, just when we talked about our vapor pressure, you want a closed system, not isolated. Okay? You don't want reactants or products to escape system. Okay? And, as you know, at equilibrium, the ratio of products over reactants. Now that will include your stoichiometry. Okay? What we just did, that's your equilibrium expression. And that's a constant. Okay? So, now that we know some of the rules behind equilibrium, that the reaction rate forward is equal to the reaction rate in reverse, that at equilibrium the ratio of products over reactants is constant, then what we need to do is start talking about properties. Again, we're going through the properties of equilibrium and how to calculate equilibrium. So, the last property is, if you notice from our expression that our equilibrium constant and the expression products over reactants depend only on stoichiometry, okay? Not the mechanism, not how that reaction proceeds. It's only on the stoichiometry. Okay, so that makes it rather nice to work with. So let's talk about evaluating my equilibrium constant. Suppose we have a reaction. I think you've seen this one. Dinitrogen tetroxide gives me 2 nitrogen dioxides. Okay, and suppose we keep this at 100 degrees Celsius, right? And then let me get you some data. All right, so the data are at equilibrium, you could have 0.00140 molar N2O4, 0.0172 molar NO2. Okay, if I did a different experiment, okay, starting off with different amounts of the dinitrogen tetroxide and the nitrogen tetroxide. So for experiment 2, at equilibrium, we get 0.00280 molar dinitrogen tetroxide, 0.0243 molar nitrogen dioxide. So, for each experiment, determine my equilibrium constant. Okay, so if we do this, then let's take a look at our expression. So whenever we do equilibrium reactions, remember our equilibrium expression is going to depend upon my reaction. So now that you have your values, we know that K is equal to products over reactant. Okay, so we're going to evaluate K. So for experiment 1, our K is going to be equal to 0.0172 squared over 0.0140. And what we get .0172, square that, divided by .0140, you get something like 0. Let's see, make sure I get my values right. 0.0172, square that, divided by .010. You get 0.0211. Oh, I'm missing an extra 0 here. That's why. Sorry. Okay. For experiment 2, 0. Products 0.0243 squared divided by 0.00280. So I get something like 0.00280. Okay, so you can see that regardless, if I'm at equilibrium, even though I have different concentrations, because I started off with different amounts of material, my equilibrium constant's the same. Okay, so before we move on to partial pressures, you're going to see a lot of different subscripts. And I think people find that fairly confusing. So let me just briefly mention how it works. Okay. When we talk about equilibrium constants, okay, really it's how we talk about it in terms of activity, which is why we really don't see a lot of we don't see any units associated with it. So we have to keep track of everything. Now, when we look at K, our values for my products and my reactants can be partial pressures, this is going to be in atmospheres, and concentrations. And this is a molarity. Now, what happens if you have a reaction that has both gases and solutions? You get the concentration. You might see us write K or KEQ, and that may represent a combination of the two. Does this happen? Yes. When will it happen? When you start looking at next semester and we start doing a lot of work with the Nernst equation. However, we're going to just focus on very consistent types of units. So we have KC, products and reactants, are all in terms of concentration. Okay. If you see other subscripts, okay, you may also see, and we're going to talk about it next, KP. All my products and reactants are gases, so we can use partial pressures, okay, in atmospheres. What about other subscripts? Yes, we do have a lot of other subscripts. So you'll encounter Ka. This is specific for acids and weak acids. Kb for weak bases. The reason I'm indenting them here is all of these are going to be expressed in terms of concentration. So a lot of these, Ksp, Kf, Kw, all of these, my reactants and products, are in terms of concentration. They're like a subset of Kc. Specifically, why do we look at these? Why do we have different subscripts? Because when we have acids, we have so many different weak acids that it's a general class of its own, and it's easier to write Ka, and then you know what you're working with. Kb, likewise. Water, so common that it has its own equilibrium constant, Kw. Kf, for the formation of complexes, you'll see at the end of 122 in the middle. Ksp, when we work with solids. Are there others? Yes. But you can see that we give these subscripts not to be confusing, but to give you an idea of the general types of equilibrium reactions that we're working with. All of these are going to have their products and reactants in terms of concentration. Okay? So just so you're aware of how you interpret those letters. Okay, the subscripts. Now that you know this, let's take a look at Kp. So, suppose we'll take our general equation. Okay, suppose we had AA plus BB goes to CC and DD. And all of these are gases. Okay? Then our expression, we can write Kp, since these are all gases, we can use partial pressures, is going to be the products over reactants that's going to be equal to partial pressure of C to that power, partial pressure of D to this power, divided by the partial pressure of A and partial pressure of B to the B power. Okay, so that's our expression for Kp. Again, products over reactants, but since everything is gases, we get to use partial pressures. Now let's go through and take a look. We know that pressure times volume is equal to nRT. So I can say that my pressure is equal to N over V RT. This is moles per liter. That's concentration. So this is the same as saying concentration. Times RT. Okay? So let's continue with this. If I rewrite this, I could also say that the pressure of A is going to be equal to the concentration of A times RT. And I'm not sure I mentioned this previously, but I better make sure that you understand. When I use square brackets, the square brackets that means concentration of. Let me give myself some space here. So I mentioned I started using it, but I wanted to be very explicit. When I have the square brackets around the A, that means concentration of A. So if I use that, I can substitute into all of this. So let's do that. So Kp is going to be equal to the concentration of C times RT. All of this is to the power of C. The concentration of D times RT to the D power divided by the concentration of A RT to the A power, concentration of B RT to the B power. Now I'm just going to basically sort everything out, do the distribution. This is the same as saying C to the C, D to the D, and then all of this is multiplied by RT to the C plus D divided by A to the A, B to the B times RT to the A plus B. So what do we do with all this? Well, this is what we do. When I run a reaction with my gases, my reactants and products are all in the same container, which means they should all be at the same temperature. So A, B, C, and D all have the same temperature. Okay, so there's no variation here. This is equal to Kc. So now we can get our relationship between Kp and Kc. And it looks like this. Kp is equal to Kc times RT, okay? And we had C plus D, okay? And since I was dividing by A plus B, that can also mean I'm subtracting A plus B. Okay? To simplify this, just call this delta n, where n is equal to the sum of the coefficients of my products. So this is the sum of the coefficients of products. Minus A plus B, which is the sum of the coefficients of the reactants. Okay? So now we know the relationship then between KP and KC.